Section 4.5, the normal distribution. Normal distribution is also called quotient distribution. And the objectives of today's video are to define the normal distribution and calculate the probabilities of outcomes using the normal distribution. Also, to estimate the mean and standard deviation of a random variable that is normally distributed. These are some examples of a normal distribution. Birth weight. The weight of a newborn baby is normally distributed. Second example. Imagine that you have to hire someone to input data into your personal database. The new hire will have to learn how to use your system. Well, the time it takes for a new typist to learn the computer system is normally distributed. Another example is the length of pregnancies. According to NIH, the mean is 285 days and sigma is 14 days. And the final example is the life in days of a light bulb. And that will depend if your bulb is incandescent, LED, or halogen. The normal or Gaussian distribution is by far the most commonly used distribution in statistics. It provides a very good model for many, although not all, continuous populations. The normal distribution is continuous rather than discrete, as opposed to Poisson and binomial distributions. This is continuous, meaning that we now have a probability density function, which is a function of x, and x is a real number. So x takes any value, not just 0, 1, 2, 3, as in the Poisson distribution. So we have two main parameters in the normal distribution. One is the mean, and the second one is the variance. And both are real numbers. Now, the probability density function is defined as an exponential function. So its domain is from minus infinity to infinity. This is the argument of the exponential. We can see that is written in terms of mu and sigma. So they are the two more important parameters. So we said that x is distributed as normal with mean mu and variance sigma squared. And of course, the mean and the variance of x are given by mu and sigma squared. So this is a plot of the normal function. It's symmetric, it's bell-shaped, and of course the integral from minus infinity to infinity of f of x dx, it should be equal to 1. Now we can see two different distributions in this example. In the first case we have this distribution with mean mu, and the standard deviation is the thickness of the bell. In the second case we have another normal distribution with sigma, in this case mu, equal to 0, and the standard deviation is smaller in this case. Let's review the exponential function to understand the Gaussian bell. An exponential function is a function of the form a multiplied by e to the bx, where a and b we are going to assume bigger than 0. So an exponential function is a function that comes from 0 and grows, and the rate of growth is very high. This point at x equal to 0 is point A. So if we replace by 0, we have e to the 0. E to the 0 is 1, so this value of crossing the y-axis is equal to A. Now, what happens if we put a negative exponent? So if we put a negative exponent, and let me do it in a different color, so we have a multiplied by e to the minus bx. Still a and b are bigger than 0. So what we have is a reflection of the curve. So it's coming from infinity and approaches to 0 as s is increasing. Now the effect of increasing b, in this case if we make b bigger, is going to be that the curvature is going to be much more concave, so it's approaching 0 faster than in the first case. So if we increase b, so this is the effect of increasing b. Now let's plot a different function. So we are going to plot function a multiplied by e to the minus b absolute value of x. So if we plot the absolute value, that means that even if x is negative, so we are going to have the whole exponent is going to be negative. So if for x positive, we are going to have the same effect of the curve in green. So this is a. And for the negatives now, because we are taking the absolute value, we are going to have the exact reflection at this point. So again, if we increase b, that will be the effect of increasing b. And on the other hand, this function is going to be symmetric. Now let's keep with the same idea, but instead of absolute value of x, I'm going to put x squared. So our function is a multiplied by e to the minus b x squared. So in a way it's similar to this, but now it's going to be like a quadratic approach to this point. So the net effect is this. So again, increasing b, this is increasing b, and this point of cut is the same, is a. Now I'm going to modify slightly the last function, so it's a multiplied by e to the minus b, now multiplied by x minus u squared. So the effect of subtracting u of u value is moving the curve to the right. So if the original one was with 0, this is 0 and this is x, so we are translating the origin to the right u times. So we are translating to u. So the effect in this case is a translation, either to the right or to the left, depending on the sign of u. Now let me express this exponential function in terms not of b, but divided by a constant. So it's going to be the inverse effect of b. So we have a multiplied by e to the x minus u squared divided by c. So we have the same case as before. So we have our function. This is u. But now c, because c is in the denominator, increasing c, it will have the opposite effect that used to have b. So Increasing c, it will be something like that. So that will move the curve in this direction. So this is increasing c, as c is in the denominator. Finally, what happens if we increase a? So we have our curve, and if we increase a, remember that a is this point, a is this point. If we increase a, we are going to have this effect. This is a increasing. Now we are going to move into Desmos. Desmos is a graphical calculator on the web, and I prepare a small demo of the exponential function. If you follow the link provided in the notes, you will open this Desmos worksheet. We can observe here the exponential function that we are plotting, a multiplied by the exponential of b multiplied by x. And we have the parameters a and b. So I will modify the parameters a and b in between 0 and 4 and b in between 0 and 3. In both cases, a and b are positive. So the exponential function is a growing function, and it cuts the y-axis at y equal a. So let's see if we change, like for example, a equal 1, we can see that is intercepting the y-axis at 1. The effect of b is going to be in the curvature of our exponential function. If I increase b, the curve is moving towards the 0. Okay. Now let's consider the following function. So we are going to have a negative exponent. So, and I'm going to plot it, and so we have both the positive exponent and the negative exponent. So we can see that the negative exponent is a reflection of the function, the positive exponent. So, but apart from that, it will behave in the same way. So if I change the crossing point, it will move for both cases, and changing the curvature, it will change the curvature. So the interesting thing about the negative exponent is that the function approaches to 0 as x increases, and it approaches to 0 really fast, faster than most of the functions. Now, what is the effect of having x equal to x squared? By changing that, so the negative part of x, it will become positive, and we will have a quadratic approach in when x is equal close to 0. So again, changing b, it will change the curvature, and a, it will change the crossing point. So now let me just forget about these two initial ones. So let's keep going with our new exponential function with a quadratic exponent. Now, what I'm going to do is change the constant b to the denominator, and I'm going to call it c. So if c and b are reciprocals, so that will have the same effect. But changing c, it will also change the curvature. So let me rewrite c for a positive factor only in between 0 and 10. So if I have, this is c equal to 0.66, very close to the original one, which will be the reciprocal of B 1.54. If I increase C, now is moving in this direction, is increasing. It's getting away from the zero. You can have an animation if it varies the values for C. Now, in this case, what I'm going to do is translating the function by subtracting x minus u. So we have u, like let's say like u equal to 0 should be equivalent to say that to go back to the original function, and if u is a positive number, is going to move to the right, and if it's a negative number, is going to move to the left. So you can have a nice animation if you just move the parameter. So I would recommend you to play with this worksheet. So follow the link and you will have access to the worksheet. Try to understand what is the effect of each one of the parameters.